Hey guys, welcome to today's video. We're learning objective today for Unit 4, 4.9. Today we're just doing part 1 of Unit 4, 4.9, redox reactions. You're going to represent a balanced redox reaction equation using half reactions. We'll talk about the activity series, and we will talk about, you'll see the 4 different types of redox reactions here. So the first thing I want to talk about is the activity series. Okay, you'll notice that the things that are most easily oxidized are going to be here at the bottom, and whatever is not so easily oxidized is going to be here at the top. Okay, so gold cannot be oxidized very easily. If your gold ring turns your finger green, it's not gold, it's more than likely copper, because copper can be oxidized very easily. Things at the bottom get oxidized the most easily. So if you have things that you put together, like if you put together copper and zinc in the same container, copper is going to oxidize zinc. Copper will get reduced and zinc will get oxidized. So, because copper is above zinc in the activity series, making copper a stronger oxidizing agent, copper is going to oxidize zinc, as you see in this first equation. The reverse reaction is not going to happen. Redox reactions do not spontaneously happen in reverse. The oxidation of iron is a redox reaction, like when it rains. Things that have iron in them are going to rust, but rust is not going to happen in reverse. Cars are not going to unrust, they're going to continue to rust. One other interesting thing is that if you want to keep iron from rusting, you can weld a strip of zinc to the iron in order to prevent it from rusting, because zinc is higher up on the activity series than iron. Alright, so here what we're going to look at is how to write a half reaction for a reaction like this, a redox reaction. So you'll see a copper 2 nitrate solution is poured over solid zinc. So we know that all nitrates are going to be soluble. So this should break into ions. So what we would have here is copper. Copper is the only species that can gain electrons or be reduced. So zinc is going to be the half reaction, that is the oxidation reaction. Zinc is going to be oxidized because it is lower on the activity series, which is why copper is going to gain the electrons and be reduced, and zinc is going to lose the electrons and be oxidized. So the half reactions are going to show what happens to the electrons and what happens to the species. And at the bottom here what we have is the net ionic equation that is balanced. Okay, what you see here is the halogen displacement redox reactions. Halogens that are bonded to themselves are going to be able to oxidize or take electrons from any halide ions below that in the family. So as an example of that, if we look at chlorine gas bubbled through an aqueous solution containing potassium bromide, we know that our potassium solutions are in general soluble based on our solubility rules. So when we look at this, we write a redox half reaction. We want to write the reduction reaction and we want to write the oxidation reaction. So to do that, okay, so the chlorine is going to gain electrons, and that's the one that's going to be reduced. The bromine is going to oxidize. Again, when we look at our halogens, everything that is the diatomic halogens, anything is going to oxidize whatever is below it. So the chlorine is going to oxidize the bromine that's below it. So the chlorine is reduced, the bromine is oxidized. And our net ionic equation for this, chlorine plus our 2 bromine ions, and we're going to have 2 chlorine ions and our diatomic bromine. Okay, our next type of our next type of redox reaction is a hydrogen displacement reaction. Okay, this is when we actually have water, and the water is going to be, the hydrogen atoms in the water are reduced because they're actually going to gain electrons. So we'll end up with hydrogen gas, and we'll end up with our hydroxyl groups. So if you look down here, this is group 1A. These are alkali metals. So anytime you have calcium, strontium, barium, or any alkali metals in group 1A, they are actually going to be able to displace hydrogen in water. And I'm going to show you an example of that. So when we have sodium metal placed in water, since sodium is on our list of things that displace hydrogen, sodium is going to displace the hydrogen. So we have our reduction reaction where our water is going to gain the electrons. So we have a hydrogen and we have our hydroxyl group, and our sodium is going to lose electrons to become sodium ions. And here we have our net ionic equation, and this hydrogen gas here, when it is let off, if the reaction is really vigorous, it can actually catch on fire. All right, so disproportionation reactions are when an element in an oxidation state actually undergoes both oxidation and reduction simultaneously. So one example of this, I'm going to write this down. So if we have chlorine gas and we're mixing that with water, we end up with hydrochloric acid and, I missed my plus sign. Okay, hydrogen chlorate. So what happens here is this chlorine we know has an oxidation number of 0, but when we have chlorine in our hydrochloric acid, it has an oxidation number of, I'm writing these backwards, of -1, and we have an oxidation number of this chlorine with a +1. So you'll see that in one case it gained electrons, and in one place it lost electrons, so it both was oxidized and reduced at the same time. So here, this X is going to represent every single metal being reacted with a strong acid. So that X is any metal being reacted with every acid except for nitric acid. That's the only one that does not work here. So the hydrogen, or the metal, is always going to gain an electron, and the hydrogen is always going to lose electrons. Okay, our final example here is to write the balanced net ionic equation for the reaction that occurs when a solid piece of magnesium is placed in a solution of hydrochloric acid. So again, we have a magnesium, so it's any metal that represents the X from our last slide, and it's going to pull out that hydrogen proton there. So we have hydrogen being reduced, and we have magnesium being oxidized. And then we have our net ionic equation. Okay, so magnesium is going to, again, magnesium is going to be oxidized, the metal will always be oxidized, and the hydrogen will always be reduced.